right. So walking through, taking a look at what you each put. Temperature of hot chocolate. I assume that it's the chocolate, like it's already hot and then it sits out. So then we would be calling that decay. So I have one group that put growth cools down. So if we're talking about growth usually means goes up, decay usually means goes down. So we would probably put decay for the temperature because the temperature would probably decrease over time, right? Can we quiet down, please? So for number 2, food left in a locker. Okay, I like this.
We said
Yeah, because it could technically be the physical amount, right? And then as it, as the food decays, right, it could actually become larger, expand, maybe get some lovely growth on it, right? Yeah, okay. So, yes, okay, I can see how you can make an argument for either one. All right. My board is frozen. Amount of money in a savings account? Personally, I think this totally depends on whether you're putting money in or taking money out, right? But if you're just talking about putting a money in and then just walking away, then it's going to grow, right? So that would be growth because the interest just continues to add and make the money grow. Okay, value of a car. Yes. So unless it's like some really incredibly special investment type of car, 99% of cars, the value of the car drops the second you drive it off the lot, right? So as a matter of fact, when you buy a car, if you buy a brand new car, the largest amount of decay is the very first day you own it, right? So you own this car, you drive it over the entrance from the car dealership, and you have now dropped several thousand in price, right? So anyway, because now it's used, right? The second you own that car, kabam, that price goes boom. Which is why, if you want to make really good, wise money decisions, buying a car that's 1 or 2 years used is a much better way to spend your money than buying a brand new car. Because brand new cars, so much of what you're paying for is that first big giant drop. You remember yesterday we talked about money, and I said your money kind of goes slow and then skyrockets up. Cars skyrocket down and then kind of level off. You want someone else to have to deal with that, and then you want to do that, right? Yeah, so anyway. Height of a bouncing ball. So obviously not position like that would be growth and decay up and down, but the overall height that it's reaching, that would be decay over time. So it looks like everybody put that. Good job. Population of a city, I like the either. Honestly, cities can go either way, right? A lot of cities grow. I see people having children. Populations, for the most part, tend to grow. Not all populations grow, though, right? People move in. That's good. I like all these comments. But yeah, some cities, people are leaving, right? And if you have a city where more people are leaving than are being born or coming in, that city on its own is going to get smaller, right? But in general, because our overall population is growing so crazy fast, most of our cities are getting bigger, right? So anyway, all right. So we all understand the difference between growth and decay, right? Big, smaller. So, all right. Today we're doing section 1-2, modeling growth and decay. We're going to spend some time talking about money. You will need a calculator today. So if anyone needs to borrow a brick, just come on up and grab one. So they're right here. They're great. I love bricks. Huh? No, you can decide how big is fine. Any kind of calculator is fine. You guys really do need to, I got the keyboard, somehow get a calculator on the road. You're welcome. If you're good, I have my own. Said that, just let me know and I'll get you another break. Wow, we have a lot of people without calculators they're worth almost nothing because you can't use them on any standard test at all.
Yeah, 84.
84s are good. You can buy them used for like $35.
What is the more easy or
84. 8 and 9 you can use on every test except the ACT. And 84 you can use on everything. But 89. Oh, they're really nice. Because the 89 has what's called a computer algebra in it, which means it'll factor and it'll expand and it'll do things in calculus like find derivatives and integrals and all kinds of stuff that a regular integral can't do. So, yeah. Okay,
I like the
here we go.
really helpful.
So, this first screen, there's nothing to write. Quiet, please. Everyone's playing with their bricks right now. Okay. The first screen, there's nothing. If your brick screen is too dark or too light, I can show you how to adjust it too if you need it adjusted. Okay. So, this first screen, nothing to write. We're just going to talk for a minute about use of 0 versus use of 1. So, see this green button? See this little like boom thing? So you hit that and hit the minus. Okay. So, yesterday we started every single sequence with use of 1. And what does use of 1 mean? The first term, right? All right. However, there are times when you might want to start with the 0th term. Why on earth would you want to start with the 0th term? So, for example, yesterday we had concert hall. There's no row 0. You start with row 1, right? First term, row 1, good, good to go, right? However, what if we're talking about money you put in the bank, which we're going to do in a few minutes? If I put money in the bank, and then, so say I put $1,000 in the bank, right? Once it sits for a year, I am now at year 1, and I've earned a year of interest. But did I start at year 1? No, I started at year 0. So, especially when you're talking about time, you tend to want to start with term 0, not term 1. Not always, but usually. For example, the day you are born, you are not 1. You're 0, right? So, and if you're counting in years, you stay 0 until you hit that first year, and now you're 1, right? So if your baby is like 8 months old, how old's your baby? 0 years, right? My baby is 0. So anyway, yeah, you start with 0. So most of the time, not all the time, but most of the time when your n value represents time, like time in years, usually you're going to want to start with a 0. And so that's why you'll see like some problems we're going to start with the use of 0. Some we're going to start with the use of 1, and just know, don't let that freak you out, all right? And we'll talk with each problem which one would be the best one to use. All right, let's think arithmetic and geometric again. So yesterday we learned 2 recursive formulas. This one on the left here, which one is that, arithmetic or geometric? Arithmetic. What does the D stand for? Common difference. This one on the right, what's that one? Geometric. And then what does the R stand for?
Ratio.
Common ratio. Common ratio. Okay. So we're going to start with the value of what looks like a flower van there from the 70s. It makes me think of the movie Cars. So anyway, an automobile depreciates or loses its value as it gets older. Suppose a particular automobile loses 1/5 of its value every year. Write a recursive formula and then find the value of the car when it is 6 years old if it costs $23,999 when it was new. So if it it should just say cost. I changed it to costs, but it should say cost because that's the past tense. You don't say costed, just cost. If it cost, yeah, $23,999. All right, So first question in your groups, I give you 15 seconds to decide if we're going to start with u sub 0 or u sub 1. Go. All right. Does everyone agree? Yeah? Okay. Your group, middle group right there. What did you guys decide? U sub 0. Do you all agree? Why? Because it's talking about time. That's a nice little giveaway, right? That you're going to do a u sub 0. It's not 100%, but most of the time. And what you can do is ask yourself, u sub 1 would represent when the car is 1 year old, right? Okay, good. So our u sub 0 is 23,999. Next question. The car loses 1/5 of its value each year. Is this going to be, you know what? I want the whole class to answer. I'm going to count to 3. So your answer is going to be arithmetic or geometric. Are you ready? 1, 2, 3.
Geometric.
It is geometric. Very good. Very good. Because we're going to be multiplying each term times something, not adding. You're not adding 1/5 each year. All right. So now your goal with your group is this is going to be something times u sub n minus 1. You got to figure out what the common ratio is. And I'm warning you, be careful, because u sub n should be how much the car is worth that year. What's the value of the car at year 1? What's the value of the car at year 2? How much is the car worth? This 1/5 is not what it's worth. It's how much is lost from the value each year. All right? So think about it. Talk about your groups for a second. See what you come up with for your common. All right, middle group. What did you guys come up with for common ratio? 4/5? Did any other groups get 4/5? Yes? Did all of you get 4/5? What did you guys get? 4/5? Okay. Yeah, it is 4/5. The reason it's 4/5, so I'm going to write, instead of writing 4/5, I'm going to write 1 minus 1/5, because this is your amount of decay. That's like your, I should call it rate of decay, but it's how much you're decaying by each year. So if you're decaying by 1/5 the value of the car, that means that the actual value is what's left is 4/5. So you end up with 4/5 u to the n minus 1. Take a second, use your calculator. I want you to see if you can find what the value of the car is after 6 years. So you're going to have to be multiplying times 4/5, times 4/5, times 4/5. And you'll have to figure out how many times you got to multiply by. After 6 years, what'd you get? Okay, say it out loud.
6,291.
And here we go. All right, so u sub 6 was around $6,291.19. Look at that. Your car was $24,000. 6 years later, it's worth $6,000. Yeah, okay, that's a pretty steep decay, though. Yeah, it's probably worth a little bit more than that. But anyway, okay. So we have been studying recursion, which means if I asked you how much is the car worth after 20 years, you got to find the value of the car for years 1, 2, 3, 4, 5, 6, all the way to 20 when you do recursion. Is there a faster way? Yes, there is. So really, if I'm finding u sub 6, I took my 23,999 and I times it by 4/5, and then I times that answer by 4/5, and then that answer by 4/5, right? How many times did I multiply the 4/5 by? 6 times, right? What you just figured out is what's called the explicit geometric formula. So in general, I'm going to rewrite these here. So yes. Okay, So I'm going to write recursive, and I'm going to write explicit, and I'm going to see if you can see the difference. So our recursive formula, u sub 0, 23,999, and u sub n equals 4/5 times u sub n minus 1. Our explicit says that our u sub n is our u sub 0 times our r, oh, here it'd be 4/5, 4/5 to the n. Now, yes?
I don't understand how you got the 4/5.
Oh, okay. So, going back here, the car loses 1/5 of its value each year. I'm not asking how much is lost, I'm asking how much is left.
Oh, okay.
So if we take the whole car and subtract like 1/5, we're left with 4/5 of the car, of the value of the car, right? Okay. So that's how we got the 4/5. All right. So this right here, this is recursive, which means it looks simple, but in order to find any term, you got to know the value of the term before it. This is called explicit, which means in order to find a term, all you need is what was your starting amount and how many years in are you going. You just plug them in. So let's just write, I'm going to give you general forms. So in general, we'd have a u sub n equals r times u sub n minus 1. That's our general, right? You have your u sub 0 or your u sub 1. But that's your general form for your recursion. Your explicit, if you start with u sub 0, your u sub n would be your u sub 0 times r to the n. If you start with u sub 1, it'd be times r to the n minus 1. If you start with u sub 2, it's times r to the n minus 2. If you start with u sub 5, it's times r to the n minus 5. But most of the time, you're going to start with 0 or 1. We're going to use these a lot today. What does R stand for again? Common ratio. Common ratio.
How do you do with an arithmetic?
We are not going to get to that until like maybe 3 or 4 more lessons. Then we'll get to explicit formulas for arithmetic.
So is u sub 0 only used for
No, there are other circumstances that you use u sub 0. I'm trying to think of one off the top of my head. And I'm losing it. I will tell you that in calculus, when you study sequences, every single sequence starts with u sub 0. There's no, even if it starts with u sub 1, you shift it and force it to be u sub 0. So that's what I'm so used to, that starting with u sub 1 feels weird to me. But it's fine. Like they're both fine. We're going to do a bunch of examples today. This one, it's going to be years. That's time. That's still time. Oh, here we go. This one's going to be one where it's not time. So we'll talk. There will be circumstances. All right. Oh, but no, that's a use of 1. It's not time, and it's a use of 1. I'm still not finding any outliers. This one, haha. Okay, we're going to hit some. So don't worry. Okay, but let's just go one at a time. All right. So this bothered me, this typing, that it said Gloria and then it switched to you. So we're just going to put you all the way through. Okay. All right. You deposit $2,000 into a bank that pays 7% interest. I will tell you right now, there is no bank in the entire world that pays 7% interest. You might have investments, right? Stocks, mutual funds, stuff like that pay 7% interest. Yes. That's pretty good. So maybe I should find an international Indian online bank.
If you do that, then it converts to rupees, and the dollar to rupee amount,
you lose money.
Goes up.
So when you convert back, you lose
You
money.
lose money. Okay. Yeah. Here you're lucky in a savings account if you get 1%, right? Yeah, it's really low. Okay. You're not going to make a fortune in a savings account, right? Savings account is a place where you want to park your money and be able to get to it quickly and easily, right? But if you're trying to make a lot of money, then you go, that's where investments come in, right? Okay, let's get off of life advice and get back to math. So, but let's just pretend we live in Wonderland and our bank pays 7% interest, right? Okay, we put in $2,000 and we're not going to touch it for 4 years. We put $2,000 in and we walk away for 4 years, just let it sit and grow, right? So we're going to write a recursive formula and what they're calling a geometric growth formula, which is what I'm calling an explicit formula. So a recursive formula and an explicit formula to represent the same situation. So first of all, are we going to start with u sub 0 or u sub 1? U sub 0, right? What is u sub 0? 2,000. So for your recursive formula, you're going to start u sub 0 equals 2,000. Now you need a u sub n, which means you need to figure out a common ratio. Be careful. We want each term to represent the total amount of money in the account. So if you take the 2,000 times 0.07, is that how much money is in the account after a year?
No.
What does that represent?
How much is being added?
How much gets added to the account? I want you to figure out an R that gives you the total amount in the account. So I'm going to give you a minute to see if you can figure out what R needs to be to represent the total amount. So this group over here, what you guys come up with? What's your R? 1.07. Did any other groups come up with 1.07? Fantastic. Did you notice on the decay we did 1 minus 1/5, and here on the growth we're doing 1 plus 0.07? Maybe because 1 is like the same as 100%. That's your whole thing, and then you want to add 7% to it, right? Before it was 100% the whole thing, and we want to subtract 1/5 of it, right? So our R is going to be 1.107% or 1.07 times our previous term. Now, if we wrote an explicit formula, then we don't have to write a u sub 0. For explicit, you just write the formula and you're done. So our u sub n would be our starting amount times our R. Since we are starting with u sub 0, would this be to the n or the n minus 1? To the n. All right. So if interest is paid, this should say once per year, not 1 per year. Oh my gosh, so many typos. All right, if interest is paid once per year, so one time a year the bank goes in and they add interest into your account, how much are you going to have after 4 years? So everyone, you can use the recursive or the explicit to figure out what your balance is after 4 years. So you're finding u sub 4. Good. So tell me what you got for, hang on, don't tell me yet.
Okay.
All right, now tell me, what'd you get for u sub 4?
I got 2,621.59
And 59 cents. Did everyone get 2621.59? Yes? Okay, any questions on plugging numbers into either formula? All right. We're going to learn something called compounding. How many of you studied compound interest sometime in the past in one of your? Good, fantastic. Okay, good. So 3 of you. Okay, quiet down. compounding is when your bank puts the interest in, well, really, they compound annually is once per year. But however often they put the interest into your account, that's called compounded interest. So most banks, like if you're doing a savings account, if you get a monthly statement or, even if it's online or whatever, you'll see something that says like interest, and that'll be, 43 cents or whatever they put in there, right? And then that'll be added to the balance in your account, right? If you get interest added every month, that means your interest is compounded monthly. If you get interest added every 3 months, then your interest is compounded quarterly, right? This problem right here, we get it every 6 months. 6 months is called semi-annually. So, different rates. There's different ways to compound interest. When you compound, your interest rate, so say our interest rate is 7%, if they compound monthly, they're not putting 7% in every single month. They're putting 1/12 of 7% in every single month. So they take the interest rate, divide it by how many times you compound per year, and that's what they do, what they find the interest on and put it into your account. How does this help you? Because then each month you get interest on a slightly higher balance, because now it's not just what you put in, but it's what you put in plus that little bit of interest, right? So every time they compound, the more often they compound, the more your money grows. Now, if you're talking about a savings account with, $1,000 and, a 2% interest rate, the compounding really doesn't make much of a difference at all. If we're talking about huge amounts of money and really big interest rates, then compounding makes a big difference, right? But when you're talking small, it really doesn't make much of a difference at all. It's pennies. So anyway, but we're going to calculate some compounding. So in order to calculate compounded interest rate, the first thing let's go ahead and we're going to kind of derive the formula, all right? So we're going to do this with numbers, and then I'm going to do this with a generic formula. So our U sub n equals, so what do we start with, 2,000? Yeah, okay, our 2,000. So now the interest rate they're calculating on is not 1 plus 0.07, it's 1 plus 0.07 divided by 2, because they're compound, the interest, every 6 months. So it's 1 plus 0.07 divided by 2, because we're doing half a year's interest instead of the whole year. So 1 plus 0.07 divided by 2. Now, since we are doing compounding twice a year, if we were to find the balance after 4 years, it's how many times did we calculate interest? So if we compound twice a year for 4 years, we have calculated interest 8 times. And that's what we put up there. All right, I'm going to give you, so this is how you would find the answer to this question, and then I'm going to give you a generic formula for the same thing. All right? All right, so everyone take a second, see if you can calculate this on your calculator.
No, I know. Why is the ratio 1? For this one, you get where did you get the 1 from? Like, do you know?
Very good.
Yeah. Obviously, you don't need that in ratio.
All right. Micah. Yeah, I'm saying right. Micah, how are you? Did you get an answer yet? Okay, I'll give you another minute. That's okay. We'll just let it run.
Oh.
All right, what'd you get? Points and 62 cents. That is perfect. Well done. Which means if we compound twice a year, after 4 years, we're walking out with $12 more, right? Woo! $3 a year more. Right? Okay, on our 2,000. Yeah. Okay. So in general, if we needed a formula for compounded interest, here's your general formula. So your use of n is going to equal your use of 0, your starting amount, times 1 plus whatever your interest rate is. I like to call it R. I hate, though, that we're letting R represent two different things. But typically here we put R for the interest rate and N for the number of times we compound per year. And out here, NT. I'm going to write a little decoder so you understand this. So our R is our interest rate.
Or growth formula, right? Is this growth?
Yes, this would be growth. You know how you know it's growth? Because it's 1 plus stuff, not 1 minus stuff. All right. N, number of times you compound per year. And then T would be number of years, right, that you're letting it sit in there. That would be your general formula for compounded interest. It's your initial investment times 1 plus your annual interest rate divided by the number of times you compound per year. So if it's monthly, it'd be 12, quarterly, it'd be 4. And then your exponent is that number of times per year times the number of years. So 12 times per year times 2 years, you're raising to the 24th power. So whatever it is. This part right here is the most, leads to the most common mistakes on calculator entry. Because if you put raised to the n and then do times t and you don't put this all in parentheses, your calculator is going to raise to the n power and then take the answer and times it by t instead of raising it to the n times t. So you have to either put this in parentheses or just multiply it before you start. Okay. All right, so see if you can use that same concept to find your balance if you were compounding quarterly instead of semi-annually. So let's see what you can do with quarterly. Quarterly? Whoa. Oh my gosh. I have 30 seconds to finish this lesson and we're not even close. All right. So use of 4 would be our 2,000 times 1 plus 0.07 over 4 to the 4 times 4. And when you do this, if you want to check your answers later on, 1 plus 0.07 divided by 4. Okay, you should get around 26, 39, 86. All right, we do not have time to talk about the next example, which is a bidding example. What I'm going to do, so for this next problem, you buy some shoes on an online site and you're immediately selling them. So you buy some shoes and you decide, I'm going to sell these and try to make a profit. So bidding starts at $100. When bidding starts at $100, that means like on eBay or whatever, you put the price, the minimum price at $100. First bid then would be $100. So that would be your use of 1, would be $100. If each bid pushes the price up by 15%, then your R would be 1 plus 0.15, the 100% plus the 15% times your previous value, so 1.15 use of n minus 1. That would be your recursive formula, right? That's your recursive formula. Your shortcut formula, which I like to call the explicit formula, would be, let's do a different color. U sub n would be your starting amount times your R. But now, since we're starting with bid 1, this would be to the n minus 1. All right, if the 10th bidder purchases the shoes, use your shortcut formula. U sub 10 would be 100 times 1.15 to the 9th. So how much money did you collect on these shoes? You collected, hang on, glasses are going on. Here. Oops. Times 1.15 to the 9th. So you just made several $100, a couple $100. You ended up collecting $351.79. So not bad. $100 investment. In a few minutes, you walk away with $350. All right, the very last thing we're going to talk about, recursive formula for the height of a ball dropped from 150 centimeters that has a 60% rebound ratio. Your rebound ratio means that each time, so 60%, that's the same thing as 6/10 or 3/5. That means each time the ball is dropped, it's going to come back up 3/5 of the way that it came up before. So if it starts at 150, the next time it bounces up, it's going to bounce up 3/5 of the way, which would be 90 centimeters, right? So, and then it's going to bounce up again, and now it's 54 centimeters, and so on and so on. So, our recursive formula, recursive are, would we start at 0 or 1? Well, I'm going to let n equal the number of bounces. But it depends on what you decide to let n be. So this, for me, would be just a drop. So this would be bounce 0, 1, 2, and so forth. So I would say my use of 0 is 150, and my use of n would be my, let's see, what is it, 60%? So 0.6 or 3/5 times my previous bounce. If I wanted an explicit, then my use of n would be my use of 0, which would be 150. Helps if I actually put in the number. 150 times 0.6 to the n minus 1. And that's it.